Hello, and welcome to Critical Thinking and COVID-19, Episode 10, Inductive Generalization. It is reasonable to wonder how the experts are determining the number of cases of COVID and calculating its lethality. Some might be concerned or even skeptical because the numbers often change and they vary across countries, age groups, ethnicities, economic classes, etc. This episode provides a basic overview of a core method of making inferences from samples to entire populations. This is what philosophers call the inductive generalization. An inductive generalization is, not surprisingly, an inductive argument. In philosophy, an argument is not a fight, a battle, or a dispute, although it can be. In technical terms, it's this. An argument consists of a set of claims, statements that are true or false, and these claims fall into two categories. There are the premises, which are the reasons or evidence being given for a claim. Premises can be unlimited in number. Now, the claim that's being supported is called the conclusion, and every argument has one and only one conclusion. So premises are evidence or reasons being offered for the conclusion, and the conclusion is the point being argued for, what one is trying to prove. Philosophers generally divide arguments into two main divisions, the inductive and the deductive. We'd engage in deduction or induction. In philosophy, a deductive argument is such that the premises provide, or are supposed to provide, complete support for the conclusion. Put another way, if you have a perfect deductive argument, what we call a valid argument, if all the premises were true, then the conclusion must be true. An inductive argument is an argument that has premises and a conclusion, being an argument, but its feature is this. The premises provide, or are supposed to provide, some degree of support for the conclusion, and this degree of support is less than complete. So, if the premises of an inductive argument support the conclusion adequately or better, it's called a strong argument. If the logic is not that good, then it's called a weak argument. Now, if the argument is a strong inductive argument, and it does in fact involve true premises, it's sometimes referred to as being cogent. So, deduction tries to offer certainty, perfect logic. Induction just gives us probability. Now, this feature of inductive logic can be seen as kind of a flaw. A strong inductive argument could still have all true premises and a false conclusion. This is because of what is known as the inductive leap. The conclusion in an inductive argument always goes beyond the premises. This can also be put in terms of drawing a conclusion from what has been observed to what has not been observed. And anytime you make a leap, things can always go terribly wrong, as various YouTube videos show. Now, our good dead friend David Hume argued back in the 1700s that this feature of induction meant we could never be sure about inductive reasoning. And later philosophers called this the problem of induction. Laying aside all the philosophical complexities, in practical terms, this means that even if we somehow made a perfect inductive argument, and we had premises that were absolutely certain, our conclusion could still turn out to be wrong, because we're making that leap. Because what we have not observed may not match what we've observed. That's just how reality works. So why do we use induction with this big flaw? Well, very practical reason. It's often the only option, so we use it because we must. So, when the numbers about COVID-19 based on generalizations turn out to be wrong, that is actually what we should expect. It would actually be surprising if we get it right the first time, or the second, or the third time. This is how inductive reasoning, works. Again, we use it because it's all we've got, the best we've got. So what is this inductive generalization I've been talking about? Roughly put, It's an argument in which a conclusion about an entire population is based on evidence taken from a sample pulled from that population. The formal version looks like this. The premise 1, the only premise, is that p% of observed x's are y's. The conclusion, p% of all x's are y's. So the idea essentially is this. You observe a sample, find out that a certain percentage of members of that sample have a particular quality, and then you leap to the conclusion that the same percentage applies to the whole population. So the observed x's, whatever they are, would be the sample, and all of the x's would be what we call the target population. As an example, if someone wanted to know the mortality rate for males over 60, the target population would be all males over 60. And the sample would be, the males over 60 that were observed. Kind of informally, what we're doing is this. We're saying, okay, we pull out a sample, we look at it, we get a particular result, and then we extend that back to the whole population. And things can go wrong because we're just looking at a small sample, and there's a whole other population beyond that. And our sample, for various reasons, may not exactly be like the whole population. Hence, the problem of induction there. Now, while the argument is simple, sorting out when a generalization is a good one can be quite challenging. Without getting into complicated statistics and methods of doing rigorous generalizations, I'll go over the basic method of assessment, so you can make some sense when the experts talk about such matters in the context of COVID-19 or anything. So here's how it goes. There'll be various factors whose presence or absence in the sample can affect the presence or absence of the property in question in the whole population. So what you want to do is make sure that your sample is representative of your whole population. Now, for example, if we wanted to determine the infection rate for all people, then we need to try to ensure that our sample included all factors that impact the infection rate. It would also need to ensure that our sample mirrored our target population in terms of age, ethnicity, base health, and so on for all relevant features of the population. Sorting out what factors are relevant can be challenging. In the case of COVID-19, experts are engaged in taking samples and doing causal analysis to try to create even better samples, to make better generalizations, To the degree that the sample mirrors the target population properly, it would be representative. Now, a sample is biased, and we want to avoid bias, we want it to be representative. It's biased relative to a factor to the extent that the factor is not present in the sample in the same proportion as it exists in the population. Put another way, a sample is biased means that it's taken in such a way that it doesn't match up with the target population. It doesn't mirror it, it doesn't, match it in terms of the relevant qualities. Now, this sort of sample bias is a major problem with trying to generalize about COVID-19. For example, one of our main concerns is the lethality of the virus. So, while the math is easy to do, a simple calculation in terms of determining lethality, getting the numbers right in terms of what percentage of people who are infected are dying is very difficult, because we need to know how many people have been infected, how many of them die from it, and as we'll see in the next episode, this can be quite challenging. Now, experts, of course, have been trying to determine the number of people who have been infected. This is done by testing and modeling, which are also inductive reasoning. In the United States, most of the testing is being done on people who are showing symptoms. And this will create a biased sample, and we'll see more of this in the next episode. To get an unbiased sample, everyone needs to be tested, ideally. Of course, realistically, probably not everyone, but at least more people. Until testing is broad enough, inferences about the lethality of the virus will be weakened by this biasing factor. There's also the practical matter of the accuracy of the tests and the determination of the cause of death. To use a concrete but entirely made-up example, if 5% of the people who test positive for COVID-19 end up dying, the generalization from the sample to the whole population would only be as strong as the representativeness of the sample. And if only sick people are being tested, the sample will not be representative, and the conclusion about the lethality of the virus will be wrong. And we'll see this in more detail in the next episode. There's also the challenge of sorting out the effect of the virus on different populations. While there'll be an overall infection rate and lethality rate for the whole population, there'll also be different infection rates and lethality rates for different groups within the human population. As an example, we already believe that the elderly have a higher death rate from the virus in the population as a whole. But until we have good data about everyone, we're not going to be able to say for sure the lethality rate in each particular population group. Now, in addition to representativeness, sample size is also very important. The larger you'd expect, the better. This brings us to two more concepts: margin of error and confidence level. A margin of error is a range of percentage points within which the conclusion of an inductive generalization falls. The number is usually presented as a plus or minus, certain percentage. The margin of error depends on sample size and the confidence level of the argument. The confidence level is typically presented as a number, although it can be done informally by saying, really confident, not very confident, not at all, etc. What does the confidence level represent when it's presented as a number? Well, it represents the percentage of arguments, like the one in question, that have had a true conclusion. Roughly put, it means exactly what it means: how confident you can be in it. So the margin of error essentially is a calculation or representation of how much your sample deviates or is likely to deviate from your population. So the bigger the margin of error, the more likely it is that it deviates. Smaller, the more likely it is that it represents the population. Now, when generalizing about large populations, and in this context, large is 10,000 or more individuals, a sample will need to be adequately representative, 1,000 or more members in the sample, assuming it's taken properly. This table that we're going to look at next comes from Moore and Parker's classical critical thinking text, which I've been using a really long time. And it shows the connection between sample size and error margin or margin of error, and this assumes a confidence level of 95%. That is to say, if you have a sample of this size taken properly, and you want to be 95% confident that you're going to get the right result, then that's the margin of error that you need. And the more you expand the margin of error, the more likely it is you'll be right. But as we'll see, expanding the margin of error comes at a cost. So looking at this table, and the objective here is not to memorize the table, but to look at it in terms of what it shows us. And what it shows us is this. The practical takeaway here is that sample size is particularly important. A small sample will have a large margin of error relative to larger samples. And the margin of error can be so large that it makes the sample useless, or not very useful, or it can lead to confusion, because if people see numbers that seem impressive but are unaware of the sample size, it can be confusing. So, for example, if you have a sample of 10, the margin of error is going to be plus or minus 30, which has a corresponding range of 60 percentage points. So, if you're going to be confident in your argument with a sample size of 10, that means that there's going to be this big margin of error. To give a concrete example, suppose we have a group of 50 COVID-19 patients, and they receive hydroxychloroquine tablets, and 10 of them recover fully. Laying aside all causal reasoning, which would be a huge mistake, the best we could say is that, looking at our handy table, is that 20% of the patients treated with this drug, of them, plus or minus 14% will recover fully. So looking at the results, we can't say, aha, this medicine is 20% effective. It would be 20% plus or minus 14%. So quite a big, quite a large range. Now, if you boost the margin of error, quite a bit, you can have absolute certainty, but say absolutely nothing. For example, if I say, 50% of people taking hydroxychloroquine plus or minus 50% will recover, that is absolutely true, but absolutely useless. So it is very important to say here that this is just a simple generalization, and that when we're talking about cures, etc., a controlled experiment or study would be needed to properly assess a causal claim, something I'll discuss in the future. Now, there are various fallacies, mistakes in reasoning that can occur with a generalization. I'll discuss those in the next essay. As always, stay safe, and I'll see you in the future.